let's get started with this week's asynchronous class with some reminders. On Tuesday, we will have quiz 1 that covers modules 1, 2, and 3. The study guide is online. Please do reach out if you want to talk about it or if anything is not clear. There will not be any quantitative questions during quiz 1. So all of the stats questions or concepts will not be included. This is only about the themes, the examples, the concepts that we've been learning in class, during the lectures, and in the readings and videos. So if you've done the readings and watched the videos and gone through the lecture slides, you should be all right. Let me remind you of one of the assignments that's coming up. Checkpoint 1 for the final group project is due on October 1st. This was a bit of a mistake on Canvas. It should have said it's due on September 17th. So I'm not going to change that, but it is really in your benefit to get it turned in earlier because checkpoint 2 will be starting pretty soon. So the last time we met, we talked about artificial intelligence as a model that varies in its abilities on a spectrum from weak to strong, following rules or probabilities. We talked about how there are various tests that have been developed to try and test intelligence of AI and its progression. We also talked about how AI is being included in many aspects of society, raising challenges and concerns, as well as potential benefits. We looked at ChatGPT as a disruptive technology for academic and workspaces, and showed that it should be understood how to use it properly. We also looked at bias and prediction as two challenges of AI that have consequences on people's lives. But today we're going to start with module 4, which is about big data and our environment. And we are going to start by focusing on big data for environmental monitoring, which is playing an increasing role in how we prepare and manage natural resources, hazards, and an increasingly volatile weather due to climate change. So we will look at the value of data collection from our environment in maintaining, predicting, and enhancing the services that the environment is providing for us. We will look at big data and how it emerged first from on-site observations at local scales, then to satellite imagery as we needed to understand change at ever larger scales. We will also look at how for certain applications, there is not enough data being gathered. And we will look at how, when this lack of information is combined with poor quality, it can lead us to the wrong conclusions, impede service provision, emergency responses, and policy making. So when we talk about monitoring, we mean processes and activities that can help us characterize and monitor the quality of the environment. We can also think more broadly about the management of natural resources, of which the environment is just one aspect. Natural resources also include what we can harvest or mine or gather from the environment, like timber, minerals, water. And the purpose is their management, maintaining, predicting, enhancing the services provided by the environment. Let's go into a bit more detail. We can think about how data is being used to make decisions about managing resources. Here, the challenge is balancing the different competing needs from a generally growing human population with a dwindling base of natural resources. Many resources can replenish themselves only very slowly, much slower than we use them, leading to depletion. By competing uses, we may mean usage for recreational purposes or grazing, timber, fish and wildlife, mineral extraction, and so on. What we are interested in is using data to help us use and allocate resources more wisely. So to give you one example of water in Arizona, we know from environmental monitoring that water is sourced from surface lakes and from groundwater, and that most of it is being used for agriculture. So the state government wants to guarantee that water will continue to be available for a growing population, and therefore needs to know how is water used and by whom in order to direct regulation. We also use environmental monitoring to improve the quality of life by warning when quality is low and could cause health impacts. And also, we use monitoring to help us design regulation to improve the situation. We know from data that air and water pollution are the leading causes of premature death worldwide, associated with 1 in 6 deaths. An example of using monitoring to improve the quality of life is through the Arizona Department of Environmental Quality, using air quality monitoring combined with weather and behavior models to forecast air pollution a few days in advance to provide an early warning system. Air quality is generally not great in Phoenix. Ground level ozone and particulate matter are produced from cars in large quantities. The desert is also a dusty place, and the sun and the hot weather make ozone pollution at the ground level an issue. But with the early warning system, it can help those with sensitive respiratory conditions to avoid exercise or being outside. Another way we use data in environmental monitoring is to monitor ecosystem services and to try maintain or enhance them when possible. Ecosystems provide certain services to human activities for free, in that otherwise we would need to pay to do those services ourselves. So for example, we may think about services like water purification, climate regulation, soil fertility, natural fibers, plant reproduction, and shade. A typical example is the service provided by insect pollinators in the agricultural sector in the US, but all around the world. For example, here you have trucks carrying beehives to almond groves to help with the pollination process. And one study suggested that every year pollinators contribute $29 billion to farm incomes. And another way that we try to use big data and prediction analytics is to create early warning systems. So early warning systems are a chain of information communication systems comprised of sensors, event detection algorithms, and decision subsystems. And one example, the most typical one, is the tsunami warning system, which is used to detect tsunamis in advance and issue the warnings to people to prevent loss of life and hopefully minimize the damage to property. A tsunami warning system is made up of two components: a network of sensors that's collecting data to detect the tsunamis, and then a communication infrastructure that transmits this information and issues timely alarms to permit for evacuation of the coastal areas. Early warning systems really saved lives. So how is monitoring done? There are two main ways. One is on-site observations and one is remote sensing. So monitoring really began with on-site observations or in-situ observations when it seemed like the problems we wanted to know about were local ones. So on-site observations, you may think about stationary sensors, like weather station, for example. But eventually, with the understanding that the different components of the Earth system are really connected in space, that one event here could really affect conditions over there, there was a growing need to increase the spatial footprint of the monitoring systems. And with the advance of technology, remote sensing became a possibility. First from aerial photography, then eventually to satellites, and now drones and aircrafts. So off-site observations, we're talking about remote sensing. These are moving objects that have sensors on them, like satellites. So let's talk a bit about on-site observations. Well, one of the earliest instruments to monitor the environment was the hygrothermograph. And this was a chart recorder that measures and records both temperature and humidity. Of course, it meant that the thermometer and the hygrometer had to have been invented already too. But this machine was invented in 1845, and a couple of decades after that, the United Kingdom Meteorological Office started to install those devices all over the UK. Because before then, collecting weather data was just a hobby from individual wealthy people. But over time, it became clear that if everybody was collecting information, there was the possibility to predict and forecast the weather. And so that was an enormous scientific endeavor, which got a jump start with the invention of the telegraph, because it meant that far away places could relay their observations to a central location where the information would feed into this model, that mental model or on paper model that scientists would try and predict the weather. Now, weather forecasting is worth $5 billion in direct benefits in the US alone, and over $160 billion in indirect disaster prevention. So weather forecasting is one of those really major data using sectors of the economy that really underpins activities in many other sectors. Like the agriculture is almost entirely reliant, and the broader economy too, if you think about maritime shipping, trying to avoid storms, or air transportation, or even predicting how much energy needs to be supplied. But over time, technology improved and remote sensing, so off-site observations, became a possibility. And so that gathering data from a distance became a very attractive possibility. And at the beginning, this kind of remote sensing came in the form of aerial photography from hot air balloons. And here is the earliest surviving photo from a balloon taken in 1860 above the city of Boston. Then remote sensing really got a boost during World War I and World War II when people realized that aerial photography could help with reconnaissance. So here's a photo taken in 1918 over France to check on the trenches. And at the same time that this was developing, people really learned that having small, fast aircrafts worked better to collect this kind of remotely sensed information. But the effect this has had is that we went from having local, kind of specific data gathering to extra local and even regional observations. But other trends were also going on at the time, like the race to go to space. And so the very first image of Earth taken from space was in 1946 by a satellite in very low orbit that you can see here. And by 1954, we had our first color image of the planet. And by 1966, when the space race was in full bloom and satellites could go further out, we have the first full disk image of the Earth. And this enlargement of the observational footprint was really important because it meant we could start to understand the Earth as a system. So observations of the entire Earth provide the data necessary for many of the sectors of the economy to operate. So let me explain a little bit about how Earth observation systems work. Basically, if this is the Earth and these are the different satellites, the satellites orbit in different orbits that have different inclinations and frequencies. And as a result, they create a mosaic of observational footprints that must be stitched together into a complete picture. There are two types of remote sensing acquisition of information. And basically, they can be divided into two different types of methods. You have something called passive and then something called active. Passive sensors, they are gathering radiation that is emitted or reflected by objects or surrounding areas. So for example, you have sunlight that is being reflected or the energy being radiated from, for example, here vegetation, and this satellite is picking up on this information. And examples of passive remote sensors include film photography, infrared, and radiometers. Then you've got active collection, which emits energy to scan objects and then measure the radiation that is reflected back to the satellite. So the most common type of active sensors are radar and LiDAR. And we've already talked about those because they're used in the self-driving cars like Waymo, because it beams energy, and the reflection of that energy towards the sensor can tell the Waymo car where the objects are. Okay, so let's go through one case study about, and this one is about providing access to the internet through satellites. So up to now, most of the internet is actually provided by cables that run over land and under the oceans. These cables are connecting different countries. And what the company SpaceX is trying to do is instead create an internet network in space through a constellation of 12,000 satellites that would cover the entire Earth. This idea has the potential to solve one of the biggest issues, which is providing services through the internet to people, especially where there is a lack of internet access. as we have seen in some of the infographics that we've been reading about. The collection of all this data has started to reveal environmental changes happening at the planetary scale. And the data is confirming that certain aspects of the Earth system are in decline or going in directions which are very negative. So for example, through this global system of data collection and satellites, we are able to know the global average temperature, and this temperature has been rising very quickly and steeply due to global warming. But at the same time, big data can help us see where there are some good news. And what I'm showing here in the bottom data set is that the use of land, the amount of land used for agricultural purposes per capita is decreasing everywhere in the world. And that's very good because agriculture has one of the largest impacts on land and biodiversity. Okay, so now I'm going to turn to two issues with big data for environmental monitoring. The first is insufficient data. In maybe no other application is insufficient data as pervasive and as consequential as weather forecasting. Weather forecasting is necessary for the functioning of many sectors of the economy, as we've already seen. Forecasting is critical for early warning to prevent the loss of lives and infrastructure damage. And in a warming world, weather events are becoming more erratic and damaging, which means that forecasting and good data are becoming even more important for future projections, for planning and resource allocation. But the issue is that in many areas of the world, particularly on the continent of Africa, data availability is very low. And when data is available, it is usually not publicly available. Satellites can help gather that information, but satellites must also be calibrated with on-the-ground measurements. So there is a real inequity in the collection of data that is having real consequences in certain regions of the world. Now, the second issue is the inadequacy of data. And big data has been used for conservation in positive ways. So, for example, identifying illegal activities or targeting policy. And one example is this project called the Great Elephant Census, which was basically the first count of elephants throughout the entire continent of Africa for the first time, using aircraft photography, on-site observations, and modeling. And what the census was able to do was to help develop cross-border elephant conservation policies, which appear to have been quite successful. Now, as with everything, big data is not the truth and depends on the quality of the data that's being used. And when we have inadequate data in terms of quality, this may lead to the wrong decisions. So here's an example from the conservation world where there was a study that used satellite images and shark taggings, as well as data of fishing fleets and gear to develop a map of areas where sharks would be at risk from the fishing industry. And I think those are all the dots you see here. But when other scientists from Australia checked their work, they found that 90 to 100% of the underlying data around Australia was actually incorrect. And so they were warning that the conclusions of the study were misleading policymakers into the development of policies for sharks in the area. So maybe this feels like a low stake type of wrong conclusions, but if you can imagine, the same scenarios are playing out in much higher stakes situations. And now the very last message about big data is that even for environmental purposes like monitoring, big data has an environmental impact if the technology is not designed to safeguard the environment in the first place. So if you take IT infrastructure, for instance, well, half of the data produced and collected is only used once. Then it is stored for future use. So for example, think of all the emails you have in your inbox that you only read once and you didn't delete and you will never open them again. Well, the storage of all these emails, the storage of all this data has an environmental footprint because the data servers, the data centers, consume electricity to keep the servers cool. So it is estimated that cloud storage is now consuming 2 to 3% of global electricity, and that the emissions from that consumption makes cloud storage on par or equal to aviation in terms of emissions. And someone calculated that each email in an inbox equates to 5 to 10 grams of CO2. And globally, we send 350 billion emails per day. So the environmental footprint of idle data is really enormous. Another example is space debris or junk that is left over from defunct satellites and space exploration. Back in 1961, it was estimated that 1,000 pieces of debris was in space. And today, that number is thought to be closer to 30,000 pieces. Now, think about the increase of satellite launches. Every year, 12,000 satellites are entering in orbit. Each satellite may last only a few years to a few decades before disintegrating. So debris is really an issue because it travels at speeds 300 times faster than a car on a US highway. So a collision with satellite or spacecraft can be catastrophic, causing damage and potentially endangering any person in space. Okay, so let's wrap up. Data is collected from on-site sensors and remote sensing for environmental monitoring and natural resources management. Big data is used to manage resources, improve quality of life, and provide early warning systems. Two major issues plague big data in environmental monitoring. The first one is insufficient data, and the second one is poor quality data. And those two problems are costing lives and damages and leading to wrong decisions. Big data, even for environmental purposes, can cause environmental damage if its development does not actively try to safeguard the environment.